Perfect.
Okay, we are at the hour, so I suggest we start on time, on schedule. I guess the first speaker, Jonathan Pober, talking about detecting the 21 centimeter signal from EOR. Johnny, do you want to take over and share your screen?
Yeah, let's see if this works for everybody. All right, well, I'm going to assume that this is visible, audible. And let me start off by saying thank you to the organizers for putting on what's been a really great conference so far. I've been on sabbatical from this chair for the last 6 months, so it's really nice to see a couple other faces and talk to people and hear what's going on out in the broader world. I'm going to be giving kind of an overview of where experiments looking to measure the 21 centimeter signal from the Epoch of Reionisation are right now. And it's a lot to cover, and there's been a lot covered already. But to start off with, I'll assume some of you haven't been in the last 2 sessions and do a little brief overview of what we're trying to do with 21 centimeter cosmology or 21 centimeter tomography. And so what we're looking at here is a simulation of the universe in a box. And the color shows the 21 centimeter line emission from neutral hydrogen. So where there's really dark regions and these white contours are there just to guide your eye. These are regions where the gas is ionized. There is no 21 centimeter signal. So the epoch of reionization is taking place here at the end of the box where these ionized regions are growing. And over here at the other end, where we see the black contours, that's where you're seeing neutral hydrogen with the strongest signal, and then a complicated evolution across the box. And so there's a tremendous amount of information encoded in this signal about the properties of the galaxies or whatever sources are driving the EOR. And I don't really have time to review all the physics we hope to constrain, but the general observable is somewhat straightforward, right? So we're going to take our radio telescope and we're going to try and actually observe that 21 centimeter emission coming from this box. And so we get 2 directions on the plane of the sky, right? X and Y. We're going to make an image for astronomers here, so hopefully that should seem pretty straightforward. But then we get the 3rd direction from the spectrum of the emission we measure, because as one side of the box, the light has traveled significantly further, it was emitted earlier in cosmic history, and so it's more redshifted. And that's why you see this evolution happening across this end of the box, where it's mostly neutral over here and mostly ionized over here. That's the epoch of reionization actually taking place. And so by measuring the spectrum, we get this 3rd direction. And that's why it's often said that the ultimate goal of what we want to do is a 3D tomographic map of all the hydrogen in the universe, not just one map, but actually getting that depth direction and that cosmic evolution along that direction. So that's all well and good. We'd love to make an image cube like this one, and we could do a lot of great science if we had one. Unfortunately, we are obscured from seeing this signal directly. Right? We're in the Milky Way. Here's a map of the Milky Way in radio. And this emission plus all the emission from all the other radio emitting galaxies in the universe obscures our view of that hydrogen signal. That's the fundamental challenge for this field, these foreground radio signals. It's not completely hopeless. It's hard. The foreground emission is as much as 4 to 5 orders of magnitude brighter than the 21 centimeter signal. But we know their emission mechanisms. They're predominantly synchrotron, some free or bremsstrahlung, and they produce spectral power laws. So as a function of frequency, the foregrounds are spectrally smooth. Whereas this simulation of the 21 centimeter signal in this plot from Vivor shows that if you look at a line of sight through the 21 centimeter signal and look at the spectrum, it's very structured. That every different redshift probes a neutral region or an ionized region or an overdense region or an underdense region, and you pick up all this structure. So even though the foregrounds are boomingly bright, spectrally they're distinct, they're smooth, and that's how we're going to hope to separate them from this small but structured signal. There are a couple further difficulties in trying to do this experiment that I want to go over before I get to kind of the status of where things are now. And these are the three: that hydrogen signal's faint, that there's a lot of other local interference, and that the interferometers that we're using to make the measurement have a frequency-dependent response. So for the first, the hydrogen signal is intrinsically faint. The experiments that are trying to measure this signal just don't have enough collecting area right now to actually make that image. There's just too much thermal noise coming from all the other incoherent radio emission on the sky. And so instead, we're going to use the power spectrum, this tool we've inherited from cosmology. It's averaged in Fourier space down to a 1D curve. And what this plot shows here is the evolution of power spectrum measured versus redshift. And here in parentheses is the neutral fraction. So when the universe is mostly ionized, the signal's low. But then at high redshifts where there's no ionization, it looks a lot like the matter power spectrum. And then has this intermediate behavior tracing the epoch of reionization. But even for a power spectrum detection, we need a lot of data. The estimates are something like 1,000 hours for many of the experiments operating now. So it's still going to be challenging to make this detection just because of the faintness of the signal. The second issue of local contaminations, I mentioned astrophysical foregrounds, but there's a lot of other radio emission and processes that interfere with radio emission. Radio frequency interference, or RFIs, one of the biggest ones. And so this is a plot from Andre Offringa comparing just how much at every single frequency of the band, how much data needs to get thrown out due to interference. Red is LOFAR, where there's kind of a baseline of 2% of the data getting thrown out. Blue is the MWA, 0.5% of the data. And so even the MWA, the Murchison Wide Field Array in Western Australia on the future SKA site, extremely radio quiet area, still throwing out a fraction of our data at every single frequency. And I think people have often wanted to think of RFI as a solved problem for this field, that particularly in the radio quiet sites, we do some flagging and we move on. But something I'll try and convince you of is that we really haven't solved it to the degree that's necessary. Also, the Earth's ionosphere is a contaminant, or at least a source of error, in that it refracts the radio waves. It can make foregrounds appear to move as a function of time and spatial position. And so it's another piece of interference in the sense that has to be dealt with. And lastly, the response of the interferometer is frequency dependent. When all is said and done, distinguishing two signals with distinct spectral signatures like the foregrounds and the 21 centimeter signal isn't that hard. We have digital signal processing. We know how to Fourier transform stuff. Even if the foregrounds are 5 orders of magnitude brighter, we could pick the 21 centimeter signal out if you gave me a box that had foregrounds and 21 centimeter signal and some noise in it. I'd give it back to you and tell you this is the 21 centimeter signal. The problem is we don't get that box. We get visibilities measured by interferometers. And so the spectral nature of the interferometer response complicates things quite a bit, complicates things in two ways. One is that the point spread function of the telescope evolves with frequency. And so you're missing different modes at different frequencies. Your sampling patterns frequency dependent. These are all ways of saying the same thing. But the effect is to give rise to this wedge paradigm that you see in a lot of the 21 centimeter cosmology literature. And we've seen a lot of these wedge plots or 2D power spectrum plots already in the last 2 sessions. But the idea is that instead of having the foregrounds nice and confined to a particular region of power spectrum space, the instrument spreads power up through much more of K-space, where we want to measure the power spectrum. The second complication is that the wedge is something that happens in an ideal instrument. It has this frequency dependence. But you also need to know the response of the telescope, its bandpass, to 1 part in 10 to the 5. And that calibration challenge is exceedingly hard. And so I'd say that's probably one of the major challenges for 21 centimeter cosmology, is getting the spectral response of your telescope out of your data. And if the telescope response is not calibrated perfectly versus frequency, it's got a little bit of scruff, then it makes the foregrounds look just like the EOR, and your day is over. So there's a lot of challenges, but let's see where we've gotten to. What sort of progress have we made in kind of the 10+ years that these telescopes have now been operating? So where do things stand? Before I get into this, I want to highlight or emphasize the large number of truly superb people working in this field. So I've got shots here from the MWA collaboration, not all EOR members, but it's the best photo I had. But the LOFAR EOR team, the HERA team, there's a lot of great people doing this work. And these photos were in happier times. For those of you who forgot or perhaps didn't know, I looked like this as little as 12 months ago, but we are still collaborating through Zoom and working together. And this is what gives me confidence, or at least optimism for this field, that we're long past the days, maybe we never were, but we're certainly no longer a community where one person shows up with a great idea and just runs away with this science. That instead, there's lots of people working hard, doing great work, and making progress. And so, I just want to say, as I go through some of the recent results, for every paper I highlight, there's 10 papers that I'm going to miss. And for every paper, there's 10 results that don't headline a paper. And, we're nevertheless a key achievement in getting our analysis to where it's gotten to date. So I just want to say thank you to everybody in the community doing this work, chipping away at this hard problem. It really makes me happy to be a part of this community. So. But this is hard. Here's, I think, the fairest way to represent the state of the art. And so we're looking now at a 1D power spectrum. Down here are some theoretical models of reionization, what the power spectrum looks like. Some of them are from Andre Messinger's faint and bright galaxies. Others are from Pagano and Liu's inside out, outside in models. This is probably where we expect the EOR signal to live, down here below 10 millikelvin squared. But there are models that are not absurd, pushing the 100 millikelvin squared level. They're out there. Up here are the limits. And so it's a mess of dots and lines and shaded regions. But to help you parse this, I think it's kind of been 2 generations of results to come out of these experiments. So the first, these dots from about 2013 to 2017 or so, excluded this gray region of this parameter space. And in the last 18 months, 2 years maybe, these lines, also some new results from LOFAR, have pushed down into this light gray region. We've gotten about an order of magnitude or more better than we had with our first generation of analyses. These aren't always new data sets, but new techniques and some new data sets as well. There's some nice work by Brad Gregg and others showing that these limits are starting to rule out some of the most extreme models where either reionization didn't happen or the gas has never been heated. There's been no energy injection into it. And so you have a very cold gas during reionization. I put those models in a different category than these ones up here around 100 millikelvin squared. These are kind of the brightest you can get, where physical processes that you expect are operating, but galaxy formation is a little bit more complicated than you thought it was, perhaps. And so we really need to get about an order of magnitude, maybe a factor of 20 lower in our limit constraints to start ruling out models of reionization that I think are at least physically motivated. And I'll note, Brenna Hazelton and others have done a lot of work to make this kind of plot. The code is publicly available. If you want to put your own limits, it's a GitHub repository, so you can add your limits, push them back up with a pull request. We can add them so everybody can have them. I think this is really a great way to represent the data because there's a lot of axes here. Redshift, K-space, power spectrum amplitude. It's tough to get everything on one plot. So as I said, I think this is the fairest way to represent where we are as a field right now. Let me show you the least fair way to represent where we are as a field right now. So this is a plot I threw together, kind of the quotable best upper limits on the 21 centimeter power spectrum as a function of time. Each color is a different experiment. I haven't labeled them, right? If you're in the field, you probably know which curve is which. If you're not in the field, that's not important. I'm not here to single out particular experiments. The open circles are results that have been retracted or otherwise superseded, that the analysis was flawed and we don't trust it anymore. This dot here right at the end, I've semi-shaded. So we heard a great talk in the previous session about some of the techniques used to produce this result. We'll hear another one later today, raising some challenges. So I'll explain that a little bit, but I think there's still some work to be done to understand whether this point is something that still stands. But this is not really a fair way to demonstrate the data. I think this is, however, a source of a lot of pessimism in the field or for people looking at the field outside. You know, as I said, these results here, the lowest we have right now, have been shown to rule out cold reionization or no reionization. But we thought we'd ruled those models out in 2015, and we thought we'd ruled those models out in 2011. And you know, all things considered, the limits that are our best limits now are about the same as the limits we thought were the best limits 10 years ago. And that's kind of, you know, it's difficult. But you know, I think there really has been progress. And that's what I want to highlight in this talk, that I really think there is a lot of reason to be optimistic about, you know, what's going to come in the next 5 years or so, as far as continuing to push these limits down and constrain those reionization models. But before I get there, I do want to say, you know, why were some results retracted? I'll warn you, the next 2 slides are probably the most text-heavy technical slides in the talk. If you've got an email you need to send or forgot to get a snack before the conference started, now might be your best moment. But for those of you who really want to know, why have we, as a community, been retracting results, it largely falls under the category of this phrase, signal loss, that in and of itself doesn't mean all that much. But what we really mean is that we had techniques to try and remove the foregrounds from our data, separate them from the 21 centimeter signal. Where you get into trouble is if you don't remove only foregrounds, but remove the 21 centimeter signal along with them. Why might that happen? So you might think of the problem as having a data vector D. You have some model for the foregrounds M. You subtract the 2, and then the residuals are where you hope to find your 21 centimeter signal. But M is not something that just gets handed to you, the model of your foregrounds. Quite often, you estimate it directly from the data you're working with. We heard about this in the last session with some of the blind non-parametric techniques, but other techniques have basically the same problem. You're estimating your model from the data. And you have ways to try and make sure the 21 centimeter signal doesn't wind up in the model. You prioritize a spectrally smooth model or an intrinsically bright model or some sort of sparsity basis. There's lots and lots of techniques out there. We've had a lot of great talks about them. But at the end of the day, it's not good enough for the expectation value of your model and the 21 centimeter component of the data to be uncorrelated. That's the statement that the model doesn't have any 21 centimeter signal in it. But expectation values are only reached in the limit when you've got an infinite number of samples. In practice, these experiments are often dealing with not that many samples. There's, particularly for some of the low resolution telescopes, there's only so many independent sidereal times before the sky repeats itself. And when your model is so incredibly bright, 5 orders of magnitude brighter than your signal, getting this expectation value to reach 0 takes a lot of samples. And so we haven't always gotten there. Another sort of repercussion is that techniques that accept the fact that the model will have some 21 centimeter signal in it will remove that 21 centimeter signal and then attempt to statistically estimate estimate how much signal was lost, you boost the limits back up. Those get very, very tricky dealing with all these cross terms. And so there's a nice paper by Karina Cheng that explores how cross terms between an injected EOR signal and your method of foreground removal actually spoke to each other and can bias your limit very low in unexpected ways. So this has been tricky, and this has been a problem that we've been running into, as I've shown you, for close to a decade now. And I think I've learned a lot of lessons along the way, but it's been a problem. I also mentioned there's this question that just came up a couple weeks ago about some of the more recent techniques. So Nick Kern's going to talk about this later today, but I want to give kind of a general overview about what the issue is. And the idea is that we need to think about the window functions of our power spectrum. And I don't mean the digital signal processing window functions. I mean the fact that when you plot a power spectrum, you put a dot saying this lives at a K mode of 0.05 inverse megaparsecs. But it doesn't really, it's not a delta function. There's a linear combination of all different sort of modes in K space that contribute to your power spectrum. And if those window functions are narrow, there's very limited region contributing to that point, then it's basically telling the truth. It comes from the space you think it's coming from. But if that window function is wide or has some long tail throughout K space, then the interpretation of what it means when you say this point lives at K of 0.05 and your ability to compare it with theory is complicated. And the point that's been raised is that that foreground removal process can change your window functions. So here's this simple equation again. If I take my data and a model that was estimated from the data to produce some residuals, well, you'd like to think you can just analyze the residuals exactly like you analyze the data, right? I've subtracted something, so I haven't changed the frequencies at which I've measured things. I haven't changed the times at which I measured things. So R has the same shape as the data. But this model that was estimated from the data can change those window functions for R compared with D, particularly if it's non-local, if it reaches out across all of K space to estimate the foregrounds at this particular location. That has complicated effects. And so I think that's something we're still trying to understand, and I'll leave it to Nick to talk more about that a little bit later today.
About 3 minutes left. So you know.
Okay, so where have we made progress? I think there's been a lot of progress in data quality. As I mentioned, ultra-faint RFI RFI is a problem. We thought we maybe had it solved, but we're finding new stuff, new techniques. We're generating new ways to find it faster as our data rates go up. There's been a lot of interest in machine learning. Array redundancy, ionospheric metrics, lots and lots of new ways to find bad data. And the bottom line here has been that the power spectrum limits go down when you get rid of more bad data. These are helping a lot. Calibration has been probably the most active area. And I think if I distill the lessons, I think we've learned if you're doing sky model calibration, comparing your data with the sky, with no constraints, trying to estimate every frequency, if the sky model is incomplete, you get large errors. And if you're doing direction-dependent calibration, that can cause signal loss with an incomplete sky model. There's hope for getting better sky models, particularly of the diffuse, but they won't solve everything. There's been a lot of interest in the field in redundancy-based calibration, but recently we've really seen in theory and in practice that if you have a good sky model, the redundancy isn't adding a whole lot. Where some techniques or some approaches have shown real progress is using the autocorrelations as new constraints. The Barry et al. And Lee et al. Limits, I think one of the biggest factors in bringing those limits down was this new autocorrelation-based spectral calibration. And I also think, filtering out, downweighting, penalizing against spectral structure has been a lot of discussion about how to make your calibration spectrally smooth. But only recently have I really started to see frameworks that do that in a statistically robust way. And Ruby will talk about that a little later. And lastly, on places we've made progress, I'll spend a minute here, even though I'm running out of time, because this I think is an important point. This plot you're not supposed to follow. You're just supposed to be scared by it. It's a software pipeline for Hera. But this is something, a conversation I had back in grad school with a philosophy professor that I was teaching with, John Campbell. And I would say to him, cosmologists don't do experiments when we talk about philosophy of science. We don't do experiments in the traditional sense, because we only have one universe. You don't get to run the universe over and over again. And he thought about this for a day or two and came back to me and said, no, that's not how you want to think about it. You're doing science in the sort of textbook sense of make an hypothesis and do an experiment to test the hypothesis. Your hypothesis is you build telescope X, analyze the data with method Y, you'll get result Z. And if the experiment is to change X or Y, the telescope or the method, and see if you get result Z. And if you don't, change X and Y again. But we don't get to change telescopes very often, but we do change the analysis. And I think this is really helped me to think about the problem, that this is where you do science, textbook science, control groups, single variable tests, good documentation, reproducibility. That's what software does for these experiments. Changing your analysis in one very controlled way, changing one step, one time. And so I think the embrace of software has been a real point of progress for the field. Okay, so I probably have about 30 seconds left. I want to give you a sense of how are we going to get that next order of magnitude? Where do we go next? And there's sort of three areas I'll go through quickly. But I think data quality needs to move to data recovery. I said we've thrown out a lot of data and it makes our limits better. But we can only throw out so much data when you need 1,000 hours of good data for a detection. And so this is an example of finding some RFI using Mike Walensky's SINS method. This is the flagging we did. We flagged all the frequencies. Well, why did we do that? Why didn't we just flag these frequencies? Or maybe we should throw out the entire observation and say there's stuff below the threshold. But getting more surgical in removing your contaminants, I think, is something we need to work on and be prepared. There's a great paper from Andre last year about the complications of sampling patterns when you do this kind of surgical flagging. But throwing out 90% of our data is not going to be the way to get to a detection. And so I think this is an area I'd like to see people continue to work in. I've already alluded to.
We've gone a little long, so if you can.
Okay, so yeah, let me skip ahead then to our conclusion. Sorry to miss those last 2 points. I know there's some people who had asked me to show some stuff, but oh well. So the conclusion, I think progress measured by those best limits alone, it's not been good. But as far as understanding how to do this experiment, we've come a long way. It is really hard. We're constantly learning why it's harder than we thought it was 6 months ago. But I think we're in good shape for further progress in the next several years with, let's say, fewer lessons learned the hard way. So sorry for going over, and I'll take questions if we have time.
All right, thank you very much. Yay. Questions, people feel free to raise your hand or type them in the Q&A section. There is one question that came in during the talk from Pranav Lamaya. How will the SKA project help in understanding reionization in more depth?
So I think the SKA will have significantly more sensitivity than most of the first generation experiments. As far as detecting the power spectrum, it's on par with Hera, which is under construction now and coming online soon. So I think it's a question of what design enables the analysis techniques to work. Hera and the SKA will have very different designs as far as antenna layouts and antenna response. And I think having those test beds right now as we try different things, see what works, that's still really important. Because one approach, there is no one approach that has worked. And so, hopefully something like the SKA will have a good sense of how to build it and have learned from these first generation experiments. But this is still a field in progress.
Okay, Leon had a question. Do you want to ask it?
Yes, can you hear me?
Yes.
Yes.
Okay. So yeah, my question is on the RFI. As of course we're all struggling with that, whether we're in a desert or in the middle of Western Europe. My question is really that RFI flagging, of course, for a long time has been done in the very traditional way of looking at it basically in visibility space and either looking whether something stands out or not. Do you really think that that is the best way of looking at RFI flagging, or maybe transforming that to a different space and do the flagging there? I think that really hasn't been done sufficiently often to transform to other spaces and look whether RFI, for example, shows up more significantly in those spaces. So do you think that this traditional way of flagging is really the smartest way of doing it?
I mean, it certainly finds a lot of the bright stuff. I don't think we stop doing it, but I think you're absolutely right that we need to think outside the box. One idea, it's a little bit different than what you were suggesting, but that I've thought about for a while is, using a lot of data science techniques to correlate RFI with all the other databases we have, flight catalogs. I think Mike Walensky's done a nice job tracking a particular RFI source to a daily flight to Kuala Lumpur. But if we actually do the correlation and some sort of matched filtering to find out, is there RFI that we can't detect with the traditional techniques, but we know that flight was still up, it's just a little bit further down on the horizon, that may let us pick out something new. And so I think bringing other information, other spaces, as you say, to bear on the problem will definitely be fruitful.
Thanks.
All right, thanks very much. We've got a minute long, and in the interest of not stealing from other speakers, there are a couple of other questions in the Q&A section. So I'm going to—
I will respond to them there.
Yeah, let's carry on the discussion there, and I'll pass it along to James Aguirre, talking about polarized imaging for reionization with an application to Hera. James, do you want to take over and take it away? You are muted.
It is not already not going as well as it went in practice. Okay, so there's my screen, and hopefully slideshow.
Great.
Great. Okay, so I'm going to talk about polarized imaging, particularly for Hera, and you'll see why in a moment. And I want to start off by saying I've highlighted a few names here of people that I think have really contributed a lot within our group and people that you may see on the job market. So Zachary Martineau is students who did a lot of work on this as undergraduates, and some of them, Kalen in particular and Gonzalo, are applying for graduate school. So, and of course, it goes without saying that Hera is a big collaboration. This work depends on a lot of people. I have not listed all their names here, but obviously can't be done without them. So here's my quick outline. Why do we care about polarization at all for 21 centimeter studies? I want to say a little bit about what we know about foregrounds, because if you're going to image, you need to know, what you're imaging. I'm going to talk a little bit about Hera, and in particular, some of the ways in which Hera is kind of uniquely bad at this. That will necessitate a little bit of an introduction to polarized interferometry. And here I'm going to just apologize in advance that if you already know this stuff, you're going to be bored. And if you don't know it, it may be incomprehensible. I'm trying to thread the needle here, and hopefully I'll hit a reasonably good balance. And then near the end, I'll talk about the things that we sort of need to do, the tools in our tool chests for being able to get this problem under control, simulating visibilities, doing precision calibration and imaging, and then sort of a quick look at the current status of Hera. So what's the problem here? Well, the problem is that the EOR signal itself is unpolarized. Okay, so we don't actually need to measure polarization. We can just go home and the talk's over. But the EOR from other things is via spectral smoothness. So anything that's spectrally structured becomes potentially a problem, because in early days it'll be hard to tell the difference between that and the actual reionization signal. And in particular, we know that linearly polarized sources can be Faraday rotated and therefore they acquire a spectral non-smoothness due to the Faraday rotation, and that can appear as cosmological signals. So here's what that looks like. If I have a magnetic field and an ionized plasma with some free electrons, then I will get a rotation of the plane of polarization for a linearly polarized wave. The phase of that rotation is given by lambda squared times this rotation measure. And my observed Q and U will be rotated relative to the true ones. If I think of this in the simplest case of a polarized source passing through a screen of magnetized plasma. And that plasma can be either in our upper atmosphere, the ionosphere, or it can be out there in the galaxy. But that lambda squared business is what does it. If you had only one source, perhaps it wouldn't be so bad. But if you have a lot of polarized sources, you run the risk of confusing your signal. And so here's sort of the cartoon picture of this, that I have my really smooth spectrum Stokes I have Faraday rotated Q and U foregrounds. And when they are measured in my EOR power spectrum, they can still be substantially higher than the reionization signal that I'm looking for. So I'm actually worried about a slightly different problem than if you're coming from the CMB, you would be worried about, which is that I'm worried about my polarized signal leaking into my unpolarized signal. So let me quickly sort of summarize what we know about things. So this is a slide that's actually a bit old, as you'll notice from the references from Bernardi and Jelic and Jelic in 2013 and 2014. But substantially, I think these things have been held up, that we see diffuse and fairly highly polarized emission basically over the entire sky. It's worse in some places and better in others. But the rotation measure tends to be less than 10 in the units of radians per meter squared, okay? Which means that it's relatively smoothly varying in frequency and is not as much of a worry for reionization studies. And we see point sources with a low intrinsic polarization, but they can be appearing in our data with high rotation measure because they're passing through the galactic ionized, magnetized interstellar medium. And that situation has improved quite a lot in terms of what we know. Sorry, let me make one other point, right? That there's a more or less direct mapping. This is not by any means a thing you should take a tattoo on your arm, but there is a mapping between the rotation measure and the K-parallel mode that gets corrupted by that. And so we are particularly interested in rotation measures that will affect K modes that we're interested in measuring cosmologically. And that probably means we're mostly worried about polarized point sources passing through the galaxy. And now we have tons of new data. So this is from Van Eck. This is LOFAR in the Northern Hemisphere. This is a map of diffuse emission. And you'll notice the range of rotation measure over here. So relatively low rotation measures like this kind of just look like more smooth foregrounds. Okay, so it's not the end of the world for reionization studies, but you want to be aware of it. It certainly is going to come up later when we talk about calibration. Having a polarized foreground can move around because of the ionosphere, for example. And we know a lot more about point sources than we knew a few years ago, where we know now a lot about the relative depolarization as we go from our anchor at L band down to lower frequencies, and some things about the polarized fraction. So, a few percent polarization is sort of a typical thing in these bands with I think one of the things that is still a little unclear is that these are relatively still, although it looks like a lot of points, it's still a few hundred sources here. So we also need to account for the fact that most sources are perhaps even more weakly polarized. These are the ones that were detected. And we're getting better maps or better confirmation of our maps of a galactic rotation measure. So we know what kind of screen our background sources are likely to be passing through. So this is from the MWA, Risley et al. Some nice work there in the POGS survey. Okay, so Hera, if you want to know, most everything you want to know is in De Boer et al. De Boer et al. In 2017, but it's a bunch of zenith-pointed 14-meter parabolic dishes. They're not beamformed, they do not track, and they're in a highly redundant array configuration, and you can read about the motivation for that in Dillon and Parsons 2016. It's very hard to photograph this array. You get some sense of it here. Because they're metal mesh, they kind of are semi-transparent when you take a picture of them. It's hard to get above them to get a nice view. And then the background is a meerkat. And I'll mention that there are sort of two phases. The initial phase was 100 to 200 megahertz with a paper-like, if you remember the paper experiment, it was a dipole-like feed and a signal chain that had a long analog cable from the antenna back to the correlator, and about 50 working antennas and their results coming out from that soon. Phase 2 is currently under construction. We've widened the frequency range. We've changed the feed in order to accommodate that, made an entirely new signal chain, including RF over fiber from the antenna to the digitizing node, and it will eventually reach 350. Depends on the day, but I think the current number of working antennas is somewhere around 200-ish, and we're currently actively working on commissioning that. So I'll have a few things to say about the new array, but mostly about the older one. So some consequences of that redundant calibration. So Johnny talked a little bit about redundant calibration and what you gain there. Is that we get relatively poor UV coverage in the sense that many baselines are repeated over and over again. And so that leads to relatively high synthesized side lobes, even if you include the outrigger antennas that are planned. And also we have a relatively small field of view, and we have a relatively small stripe of the sky that we're going to observe here, centered at declination of about -30. Okay. Having said that, we are sensitive to the entire sky. The side lobes of the primary beam are bad enough that we see galactic emission all the way down to the horizon. So we really do care from 60 degrees north all the way down to the pole. So that makes our imaging situation, I think, rather challenging. Perhaps not uniquely challenging, but challenging. I'll just remind people that we are going to talk about Stokes parameters. So I'm thinking about measuring unpolarized Stokes I and linearly polarized Q and U. I'll have a few things to say about Stokes V, but mostly because it's an indication that you've done something wrong. And I need to fully characterize my antenna pattern as a vector response to radiation coming from both orientations of the vector. And so when I write down my full measurement equation, I need to include the direction-dependent antenna-based terms. And you notice that I've written this as an integral. I said, here's my coherency, so that includes my images of Stokes I, Q, U, and V. This is my direction-dependent antenna pattern. And I really have written this as an integral because we don't seem to be able to just say that the emission that we see is due purely to point sources. We can't express this as a sum over individual discrete sources. We see a lot of emission from the diffuse, and so we have to sort of build that into our model. A more traditional version of this equation would also include the direction-independent gain terms in the Jones matrices for the individual antennas. Then that's your traditional calibration terms here, which I've pulled sort of outside the integral. And I'll skip this for the sake of time. Those that are interested in the math can go back and look at it. So we've done a fair amount of work into simulating these beams for Hera, a lot of electromagnetic simulation in CST, Microwave Studio, and then a subsequent verification of these things with test beds and with S parameter measurements and everything. So what I'm showing here is the complex Jones matrix, absolute value in phase of the two components of the feeds. For both our old phase 1 dipoles and our new phase 2 Vivaldi feeds. And you'll notice that they do in fact behave much like diffraction limited beams with the 14-meter radius and the dipole pattern imprinted on them. But there's complexity there, and this obviously has frequency dependent structure, which I'm not showing here. This is sort of shown as a nice sweet spot in the band of about 150 megahertz. Representing these beam models in a nice way, I will just mention, is something that you really should think about doing as sort of fundamentally it's a vector field on the sphere. So you should think about it as a spin 1 representation. And so actually this nice interpolation spatially and spectrally that I'm showing here was my work from my grad student to write these as spin 1 objects and fundamentally evaluate them in harmonic space, which is a really convenient way to do it. So we can build a visibility simulation off of that fully polarized model. And the image I'm showing here is actually taken from a paper that's not really about polarization so much as it is about simulating the end-to-end pipeline. So that's coming out soon in support of our upper limits from first upper limit papers from Hera. But my point in showing this slide is just that whether you think about this in frequency time space for a single visibility, or you think about it in our various Fourier transform spaces, we're able to capture a lot of the qualitative features that the combined foreground diffuse emission plus the beam are putting into the data, as well as some systematic effects, which I'm not going to talk about here. So there is still some real work to be done in getting quantitative agreement, and I'll say more about that as we go on. But qualitatively, we do a lot of things right with our visibility simulation, and there's a number of efforts within the group. I've highlighted one from my student to make high quality visibility simulations. We've been calibrating so far under assuming that the instrument is unpolarized. So we've not been taking into account the full Jones matrix. And you can see the results in the current et al. Absolute calibration paper do pretty well. Stokes V looks mostly like noise. Stokes Q and U have some leakage in them from sources, and Stokes I, because we've not corrected for the primary beam, nor have we correctly calibrated the phases between the two feeds, which really affect Stokes Q and U and V, sorry. So let me go back and say, well, what would you do for those that don't know? If I reformulate my matrix equation instead of 2x2 matrices, which is a little bit hard to think about in terms of the Stokes parameters, in terms of a 4x4 matrix, here I can think about what I actually measure over here on the left in my visibilities as being some mixed up combination of the IQ, U, and V that are actually present on the sky. And so my deconvolution process, which ordinarily in radio interferometry, you have to deal with deconvolving the synthesized beam. Now we also want to undo the effects of the primary beam in order to get back at what the true Stokes parameters are on the sky. So here is an example of what this looks like for Hera from the dipole feed. And I just want to point out that there's our linear polarization leaking into Stokes I. And that's Stokes I leaking back into the linear polarizations. And in fact, this is the images that I'm showing here are IQUV from the Cohn et al. Paper. And these are simulations. So this amount of leakage is actually not something that's due to improper calibration. It's sort of a fundamental thing we see because of the leakage through the primary beam.
Just under 3 minutes to go.
Great. So I will skip through this figures of merit for how can you say whether you're building a good feed. We looked at this a lot in the early design stages, and I would say we still have a lot of problems compared to other ways of building a beam, including beam forming, but I won't go into great detail here, nor the conditions here. So here what I'm doing is just comparing on the left, I, Q, U, and V image from real data in the pseudo-Stokes basis, and on the right, the simulation. So there's not supposed to be any V. That's a direction-dependent gain error problem. But some of the features that you see leaking through are actually results of the beam. So other people have the same problem. What do they do about it? Well, the bottom line is you need to take account of the beam. Either you do your deconvolution or after you've created your image to fix it in post-production. So you're trying to invert this matrix here in some way, either by forward modeling or by directly inverting in the image space. So here's an attempt to sort of do that in the image space. And importantly, I think what this is supposed to show is that Fornax is still a problem. We haven't deconvolved it properly, but there is a known polarized point source here that we have correctly identified in I with the right flux and Q. And there's a problem with U and V that we've not properly calibrated the phases here. And I'll just say, not super relevant to polarization, but we do have a lot of data sitting in the can from Hera. And so we have a lot of ways of looking at how things are changing and how stable they are, which is interesting when we come to the ionosphere, because that's a natural source of time variability in your data. And in order to really properly model it, you need to put it into the direction-dependent integral here. But in fact, the ionosphere is often quite constant spatially. So if you're restricted to a relatively small field of view, as a first approximation, you can treat it as constant and fix it in the images again after the fact, which is sort of, I believe, what is shown here for MWA data. Okay, pressing on, and that can be done. It also provides a way of testing whether you have polarized leakage. Take a bootstrap of different parts of your data with different rotation measures as seen by the ionosphere, and see whether the strength of the signal changes in your power spectrum. And we talk about that a little bit in the Martineau paper if you're curious about that. So here's what it looks like in real data. We've actually seen this. On the left is east and north polarizations, and then the Stokes Q and I and Q power spectrum. You'll see this streak here. And in fact, if you look at it as a function of spectral window, you see that it evolves with spectral window. And lo and behold, evolving with spectral window is exactly what is the problem, that the rotation measure of the source is showing up as some delay and therefore some K mode. And if you then properly speak of this in rotation measure space, then you see that there is a known pulsar here with a rotation measure of about 150 from the galaxy. And indeed, we've seen that now with Hera. So what are we going to do about that? The problem...
Time, so if you can wrap up.
Okay. So I will skip really quickly through the current status of looking at the new instrument, but we have sort of similar problems in which we're trying to compare simulations to reality and look at how well they match up against one another. So my conclusions there, I've done, I think, a good job of matching simulations of the instrument and the visibilities to data, although not perfect. I think, in giving this talk and preparing it, I realized there's a lot of sophistication out there that we've not really brought to bear on Hera, which clearly we could do. And it's not entirely clear what to do here because we're never going to make high quality image cubes in the same way that LOFAR, for example, does. So we are going to have to tackle polarization kind of on a ad hoc basis to try to figure out how to mitigate it as best we can. Okay, since I'm over, I will stop and leave the slide there.
All right, thank you, James. Great. We have time for maybe one quick question. There are a couple of questions typed into the Q&A, but I might leave those for answering offline just because that can be typed. So is there anyone who wants to ask a very quick verbal question? Going once, twice, 3 times. Okay, in the interest of getting a little bit back on schedule, I might just suggest then that the Q&A moves to the typed section. But thank you again, James. Very interesting stuff.
Thank you.
And we'll press ahead to Pixie. Do you want to take over and share?
Thank you, Keith. Okay. So my name is Pixie Starr, and I'm going to be talking with Byrne Hazelton about improving MWA EUR0 limits by correcting digital nonlinearities. So just to give an overview of what I'm going to be talking about, I'm going to present the problem of nonlinearities introduced into the MWA data from a digital quantization. I'll then talk about our solution to that problem, the problem with our solution, the solution for the solution, and then I will pass off to Byrne to see power spectra comparisons and results. So the problem. I'm sure that all of you are thinking right now, but the MWA has 4-bit quantization. Surely the effects of that would be negligible. Well, what we actually find is that this low-level nonlinearity that comes in from the digital quantization interacts significantly with the strong spectral structure that is introduced by the polyphase filter banks. So what this can look like is that after removing that spectral shape from the polyphase filter banks, we are left with a residual that is time dependent. So here we can see a residual polyphase filter bank shape that is varying night by night. And in particular, we can see that these periodic peaks and troughs, that distance between them or the depth of the trough is changing on this nightly basis. So Nicole Berry looked at this and then decided to plot that depth of trough as a function of temperature. And we see this really strong correlation that shows up. Now we know that our LNA gains are temperature dependent, and this correlation really indicates this complicated dynamic and interplay between those temperature dependent gains, the spectral structure from the polyphase filter banks, and this nonlinearity coming in from digital quantization. So to summarize, our problem is really these significant interactions between this nonlinearity due to digital quantization and other artifacts of the signal pathway. We know that these interactions have a temporal variation, and so that means that in order to correct them, we're going to need a time-dependent solution. Why does this matter? These effects are small. We see them showing up as a part in 10 to the 3. But as Jonathan mentioned earlier, in order to measure the EOR signal with our power spectra, we have to obtain calibration solutions that are accurate spectrally 2 apart in 10 to the 5. So though these effects are small, they still carry significance in our ability to measure the EOR signal. Fortunately, there is a solution for this problem. Van Vleck and Middleton have studied this problem of digital quantization and its effects. And Vankovich wrote down some formulas specifically for the MWA 4-bit quantization. I'm not going to go into the math behind these equations here. I have a couple of memos reviewing the math and discussing my implementation, and links to those, as well as information about Vankovich and Van Vleck's papers, are all on the reference slide. So right now I'm just going to show you these equations. For autocorrelations, we have a relation between the autocorrelation of our quantized data, and the expected autocorrelation had that data not been quantized. Similarly, we have a relation for cross correlations that relates the real or imaginary part of our cross correlation with quantized data to the corresponding part of the expected cross correlation had the data not been quantized. So this seems great. We have some equations, we can write them down. It may seem as though we could easily take our correlation data of quantized values and run it through and quickly obtain our resulting corrected correlations. Unfortunately, like many solutions, it is not quite that simple. And that is because both of these equations are not invertible. So obtaining the corrected value requires something like perhaps a lookup table or an iterative solver to get to the correction. For the autocorrelation equation, this is fine. We don't have so many autocorrelations in the data, and the equation is pretty straightforward to solve using an iterative method. But for the cross correlations, we run into an issue. A 2-minute observation of MWA data can have on the order of 10 to the 9 cross correlations, and each of those requires an individual correction. So while reading in one of those observations using PyEV data takes about 12 minutes, applying the Van Vleck correction to that observation takes about 5 hours. And with the number of observations that we require to make our power spectra, this amount of time is simply untenable. So we came up with a solution for our solution, which is to use a Chebyshev approximation for that cross-correlation equation. That equation actually depends on a couple of parameters. And so we created, for each of the first 3 odd Chebyshev polynomials, a 2-dimensional parameter space for the coefficient. Then to obtain the correction, we do a 2-dimensional interpolation over each of those grids to get the coefficients for each cross-correlation and do the correction. We tested this by taking a subset of real data as well as a set of simulated data, ran the Chebyshev approximation correction as well as an integral solver correction on both, and compared the results. That comparison found that they agreed to an order of 10 to the minus 10, which is sufficient for our needs. Finally, applying this Chebyshev approximation correction to our single 2-minute observation only takes about 20 minutes on top of read time, making it possible for us to correct our full data set for the power spectra. So now we can apply this correction. What does that actually look like on the data? So here I have an autocorrelation for a single MWA antenna. This purple line has not had the Van Vleck correction applied, and the orange line has been corrected. We can see a couple of artifacts from the nonlinear interactions with other effects. In particular, at these light gray lines, we see artifacts from that spectral structure due to the polyphase filter banks. And at this discontinuity, we see an artifact remaining after we've divided out our gains. Without the Van Vleck correction applied, these effects are definitely worse. But after applying the Van Vleck correction, we still see some lingering effects which indicate that there is a nonlinearity that is still present in our data. So I did some digging. Like most instruments, the MWA has multiple quantization stages. And also, probably like most instruments, not every bit of the digital pathway is implemented exactly perfectly. Recently, McSweeney pointed out that in one of the MWA polyphase filter banks, a rounding stage is actually implemented asymmetrically. That is, the positive and negative values are actually rounded differently in this stage. I've done some simulations looking at this and see that in addition to the nonlinearities that come in just from the rounding itself, we see some other artifacts coming in due to that asymmetry. So currently I am working on a second stage of the Van Vleck correction, which will correct for this rounding stage on top of the one that has already been corrected. So to conclude my portion of this talk, I have implemented a Van Vleck correction for the MWA. It is in the publicly available open source code base, PyUV data, and it is implemented as part of a reader which ingests raw MWA correlator files and additionally, optionally applies some other digital corrections as well. Currently, I'm working on a second stage of this Van Vleck correction, which will address artifacts due to an asymmetric quantization stage. Now I'm going to pass you over to Byrne so that you can see the impacts of these corrections on our EOR science.
Great. Just under 5 minutes left, Byrne.
Perfect. Thank you, Pixie. So in order to understand what this does in the power spectrum space, which is of course our final metric, we've processed a single night of data so far. We're working on processing more. And we're comparing that to the same day of data from the Byrne et al. 2019 analysis. Actual integration varies slightly due to small flagging improvements, and we also use a slightly updated calibration approach. We follow the Lee et al. Approach, but it's very similar to the Byrne approach. And I'm going to show some power spectra here for calibrated dirty image cubes. So these do not have any foreground subtraction, and just the XX instrumental polarization. So these are the 2D power spectra. Unfortunately, Johnny's already told you a little bit about how to read these. But I want to point out that these are cross power spectra. So they can go negative when the power is low enough, it's close enough to the noise level. So the noise, negative pixels are purple. And so noise dominated regions are fluctuating between the purple and the sort of yellow-green color bin to bin. There are some horizontal streaks in the window that you may see. Those are from the residual polyphase filter shape that Pixie discussed earlier. You can see that they're worse on the left side from the Byrne et al. Subset. They've gotten better with the wavelength correction, but they are still present, as you could tell from her frequency plot. So we're hoping that'll get better with her second stage. And also you can see there's a noticeable drop of power in the EOR window. We've got more noise dominated regions, especially sort of on the left side of the plot and then toward the bottom, which is a really critical area because the EOR is brightest toward the bottom left of the plot. So next we'll show you this in a 1D space where we've averaged spherically. So the black line is the Byrne et al. Subset and the blue line is the Van Vleck corrected, and the dashed line shows the 1 sigma thermal noise. You can see here that, again, that the lines from the polyphase filter shape have dropped somewhat, and that the areas between them has also dropped. And critically, that area below the first one of those lines has dropped, and that's a really critical area for detecting the EOR. We are currently working on integrating over the full Byrne et al. 2019 data set so that we can see what this looks like on a longer integration. And then we're looking forward to seeing what happens with the next stage. So just to conclude, the first stage of the corrections for the digital nonlinearities in the MWA data has been implemented by Pixie and PyUV data. So it's available to anybody who'd like to use it. Correcting for those nonlinearities improves the power spectrum, which is great. I want to highlight that I think this is not just a problem for the MWA. Small digital nonlinearities are very common in digital systems. And we have seen in several other systems that similar kinds of effects, slightly different, but similar kinds of effects can cause spectral features that are significant on the scale of the EOR power spectrum. So there's been a lot of focus in the community in the last couple of years about the smoothness of the analog response, making sure that the antenna response is really smooth with frequency. And I think we need to pay equally close attention to the digital response. And I think sometimes that has not been as deeply discussed and thought about because we tend to think that the digital is sort of a solved problem and it's easy. And I think we're realizing that it really matters on very low levels that we hadn't worried about before. So please stay tuned for the next set of corrections and a longer integration. Thanks.
All right, thanks very much. Well done to both. I will open it up for questions. If anyone has any questions, feel free to type them in or raise your hand. There is one question posted. First, a compliment. Fantastic analysis there, Pixie. We have seen nonlinearities due to our 14-bit ADCs in LOFAR as well. Is your ADC single stage or double stage?
So the nonlinearity that I'm actually working on is the final quantization stage that happened just before correlation. So our ADC, I believe, is 8-bit for the MWA, and then there are a couple more quantization stages down to 5-bit, some intermediate stages in the polyphase filter banks, and then finally to 4-bit before correlation. And so we're kind of working on the assumption that the 4-bit is the strongest effect, but it's also clear that earlier stages have an impact as well.
So it's a single stage ABC, but there's a two-stage FFT.
Other questions? I guess I'll ask a quick question. Do you have a sense, do you think that this residual nonlinearity is likely to be corrected once you fix the asymmetric rounding, or account for the asymmetric rounding?
I certainly hope so. There are, like I said, other additional quantization stages, but ideally this next one would be enough to not need to walk back to, say, the 5-bit quantization. There are some artifacts that we see specifically due to this one with the asymmetry, and so I'm hoping that those at least will be completely resolved and that the remaining nonlinearity will as well.
It's a kind of a case of, you can only know about the bug that you can see right now, but simulations are making us optimistic that we may be able to get it down to the level we need.
Great. Okay, so no known residual problem.
Not yet.
All right. Thanks very much. We'll carry on to the next speaker. I've lost my window. Next up is Ruby. Do you want to take over and share?
All right, can you see that?
Yep.
Okay, so my name is Ruby Byrne. I am currently finishing up my PhD at the University of Washington, and I'm going to be discussing unified calibration, which is a new calibration framework that we developed to enable precision calibration for 21 centimeter cosmology and EOR science. So this is just a really brief outline of my presentation. I'm going to give some background. Then I'm going to talk about established calibration approaches and present the math behind those, and that will bring me to this new work on unified calibration. So starting off with the background. Before I go into anything else, I'd like to define calibration to make sure we're all on the same page. So I would define calibration as a process of determining the instrument's response to the sky so that the sky signal can be accurately reconstructed. And so more specifically, this involves fitting parameters of an instrument response model according to our prior knowledge of the data and the sky signal. And these parameters are fit by maximizing a likelihood function. This likelihood function could be explicit in the calibration formulation. It could also be implicit. A really common thing that we see is that calibration minimizes a chi-squared function. And this is exactly equivalent to maximizing a Gaussian likelihood function. So this is a bit of a schematic of the calibration process. And so calibration involves trying to reconcile real data with simulated data. So the data pipeline takes the true signal coming from the sky, propagates it through the instrument to derive data. The simulation pipeline takes a model of the sky, propagates it through a model of the instrument through some sort of simulation package, and drives simulated data. And then that process of calibrating is taking tunable parameters in that instrument model and adjusting them to try to get agreement between the data and the simulation. So there's a lot of different options and choices and improvements that can be made in calibration by, for example, choosing a different sky model to input. And there's been a lot of recent work, including my own work, developing better sky models as an input. Also, there's a lot of choices that need to be made about what exactly the instrument model is and how that simulation is performed. We have to choose what parameters in that instrument model are going to be tunable. And then there's also choices that need to be made about what it means for the data and the simulation to agree. And this is more of a statistical choice. So why is calibration important? I don't need to go into too much detail on this slide because of Jonathan's excellent introduction at the start of this session. But calibration is critical to radio interferometry in general. If you have an interferometer and you want to image the sky, you need to calibrate it. But specifically, like Jonathan said, the success of 21 centimeter cosmology and EOR science really hinges on calibration because it requires that we can differentiate between the foregrounds and the signal that we're interested in. And this differentiation allows us to remove those foregrounds that are 4 to 5 orders of magnitude brighter than our signal. The foregrounds are removed by filtering out spectrally smooth signal. And the reason calibration plays in here is that calibration errors introduce spectral structure into the signal. So this is going to take those spectrally smooth foregrounds, make them no longer spectrally smooth, and just smear all their power across the power spectrum modes where we expect to be measuring cosmological signal. And so for this reason, calibration error is a major systematic that we have to contend with. And precision calibration is a major area of research as we try to improve our EOR and 21 centimeter cosmology results. All right, so what is the current state of the field? So currently there are many calibration implementations. They use different approaches and assumptions and algorithms. There's been significant work studying and characterizing sources of calibration error, and current calibration approaches do not and cannot achieve the required precision. So I would categorize the current state of the field as kind of a dichotomy between two different broad calibration approaches. So these are each kind of umbrella categories of calibration approaches with a lot of variation within them, but they're broadly categorized as either sky-based or redundant calibration. So my recent work, this unified calibration framework, represents filling in the gulf between these two approaches and allowing us to work in an intermediate regime between sky-based calibration and redundant calibration. And it also just represents sort of an expansion of the types of frameworks that we can use in calibration. So it really opens up the flexibility and the responsiveness to physical instrument models. And I'm just going to point to this paper. It's currently in review. We hope to have it published soon. And a preliminary draft is up on the archive. So if you're interested in this work, I encourage you to check it out. Okay, so that's some background on calibration, and that brings me to going into a little bit more depth about established calibration approaches. So these established calibration approaches follow from the measurement equation. So the measurement equation relates our measurement, the actual visibilities, which I'm denoting V here, to the true signal coming from the sky, which I'm denoting U. And here the subscripts A and B are just indexing antennas. So the measurement equation parameterizes our uncertainty on the instrument response as antenna gains. So these are a single complex number per antenna. I should also note that this whole equation is per time step and per frequency. And so the gains as well are per time step and per frequency. And then we also have a noise term. So to build a calibration framework, we kind of need to ask and answer 4 questions. And I'm going to revisit these questions throughout the presentation as I compare different approaches. So the questions that are fundamental to a calibration framework are, what are the tunable parameters? What are we allowing to vary in our instrument model? What is the visibility model that we're using? What is our model of the thermal noise? What do we expect that distribution to look like? And what is the prior on the calibration parameters? So sky-based calibration, which is probably the most established calibration approach out there, uses model visibilities, which I'm denoting M. These model visibilities are generated from a sky model and an instrument model. And in the measurement equation, we just say that these model visibilities well approximate the true sky visibilities. So we just replace those true sky visibilities with the model. So again, going back to these 4 questions, the tunable parameters in sky-based calibration are those antenna gains, the Gs. The visibility model just follows from the measurement equation with those model visibilities. We generally assume that thermal noise is Gaussian, and we use a flat prior on the calibration parameters. Sky-based calibration works best for imaging arrays with good UV coverage. I'll note that it requires an excellent sky model to achieve really precise results. And sky model errors introduce calibration errors that are at a level that can swamp the EOR signal. So redundant calibration is the other established calibration approach that I'm going to discuss. And redundant calibration works for highly regular arrays. These regular arrays have many repeated baseline vectors. We can divide up measured baselines into repeated or redundant baseline sets, and we expect that baselines within these sets measure the same sky signal. So going back to that measurement equation, we can now take the true sky visibility and replace it with just a single number per redundant baseline set. And this allows us to constrain this without a sky model. However, I will note that without a sky model, the solutions are degenerate. And so this means that redundant calibration has to consist of two steps. So first, we exploit the array redundancy in order to constrain the solutions with degeneracies. And then after that, we apply absolute calibration to constrain the degeneracies and actually get physically meaningful calibration solutions. So these 4 questions for redundant calibration: what are our tunable parameters? We now have more tunable parameters. We have both the antenna gains, but we also have these redundant visibilities, which are a single number per redundant baseline set per frequency and time. Our visibility model, once again, follows from the measurement equation. We can assume Gaussian thermal noise, and we have a flat prior on both the gains and the visibilities. So like I said before, redundant calibration works only for regular arrays. It can experience errors from antenna position errors and beam inhomogeneities. And so if you have any effects that break the redundancy between baselines and redundant set, this can introduce errors into the calibration solutions. But it also experiences some sky model errors from the absolute calibration step. And this is the subject of a recent paper we came out with. Okay, so this brings us to the next stage. What is this intermediate regime between sky-based and redundant calibration? So what are we missing when we talk about just this dichotomy between sky-based and redundant calibration? Well, we don't have a good method of calibrating hybrid arrays that have both redundant and pseudo-random subarrays. So the NWA phase 2 is a great example of this. It has 2 redundantly calibratable hexagonal subarrays that were developed for the phase 2 upgrade, but then the rest of the array is a pseudo-random array. And so we would like to have a statistically rigorous way of calibrating both the pseudo-random and redundant elements consistently. We also don't have really good techniques for doing redundant calibration in the presence of imperfect redundancy. So on the right, there's just a rendering of what Hera might look like when it's fully complete. So Hera is an extremely redundant array. It has many, many redundant baselines. It's very regular. But we do expect there to be some deviations from perfect redundancy, just from slight position offsets in the antennas, and manufacturing variations can give the beam response shapes variation between antennas. Another thing that isn't captured in these established approaches is covariant calibration of baselines that overlap in the UV plane but are not redundant. So this is a thing that we experience with highly compact arrays. For example, the MWA has a very compact core, and that means that there are a lot of overlapping measurements in the UV plane. And these overlapping measurements are correlated, but they might not be redundant or even nominally redundant. The baseline vectors might not be the same, but because of the finite size of the antennas, they have some correlation. And also, we don't have a middle ground between sky-based and redundant calibration with established techniques. And so this brings us to this unified calibration framework, which provides a very generalized framework that can accomplish all of these things. So now I'm going to talk about our work with unified calibration. So I'm specifically going to focus on one implementation of unified calibration. So like I just said, it's very generalized. And I point you to the paper if you're interested about all of the implementations and variations on unified calibration. I'm going to talk about one simple case where we can use some of the tools of unified calibration to do a new type of calibration. So the tunable calibration, or the tunable parameters in unified calibration are the same as for redundant calibration. We have antenna gain parameters, and we also have redundant visibilities. The visibility model, again, is the same as for redundant calibration. It follows from the measurement equation. We're once again assuming Gaussian thermal noise. But the key point here is that we do not have a flat prior on our tunable parameters. We have a prior on the U parameters, the redundant visibilities, that is not flat and uses the model visibilities. So to talk about how this is actually implemented, we need to talk about Bayes' theorem. So Bayes' theorem relates the likelihood function to the data distribution and the prior. So our likelihood is just the product of our distribution and a prior on our tunable model parameters. In unified calibration, we use a Gaussian prior on the tunable parameters U that upweights solutions that align U with the model visibilities. So M here again is the model visibilities that we develop with a sky model and an instrument simulator. And then U are tunable parameters, but we say that our likelihood is higher when those tunable parameters are close to M. So comparing this to each redundant calibration and sky-based calibration, redundant calibration is identically the limit that we take the width of that prior to infinity. So we say we have a flat prior on U, we don't know what U is, and we freely fit it. Sky-based calibration is the opposite limit. So sky-based calibration is identically the limit that we take that prior to a delta function. We do not allow U to vary at all. We don't have U as a tunable parameter in sky-based calibration. We just use M. Okay, and so I've explored this implementation of unified calibration in a simulation. This is a very simplified simulation. We use just 36 circular aperture antennas in this regular close packed array configuration. We assume perfect redundancy. We simulate visibilities from the Gleam catalog, and we perform the simulation with the PyUVSim open source simulation package. We also introduce injected Gaussian thermal noise in the simulation. We also simulate model visibilities, and we represent model visibility errors by simulating only Gleam sources that are brighter than 100 millijanskis. And so we've omitted all of the dimmest Gleam sources, and this introduces errors in our model visibilities.
Just under a minute.
So on the, sorry.
Just under 1 minute.
Oh, okay. I will speed up a little bit. So on the right-hand side, this is just a scatter plot of the errors on those visibilities because of the missing faint sources. So the white plus sign is the position of 0 error, and then all of the X's are the simulated model visibility errors. The black circle is just representing the standard deviation of those errors, and then the blue dashed circle represents the standard deviation of the injected thermal noise that we'll include in simulation. So we also include covariances in the prior. So our prior need not be independent between different U's. And because we have a close packed array, we can represent the fact that neighboring baselines detect correlated signals and include this. So these are the solutions from the simulation. If we plot the calibrated gains that we achieve, in simulation, the true gains are 1, and so any deviations from 1 represent errors in the calibration solutions. So here we've calibrated with 3 different methods. On the left-hand side, we have redundant calibration. On the right-hand side, we have sky-based calibration, and then in the center, we have unified calibration. And we can see that for each redundant calibration and sky-based calibration, we have an offset from the true values. For all of these approaches, we have a distribution of solutions But for unified calibration, that distribution is slightly more compact. And so this gives us compelling evidence that unified calibration can improve on redundant calibration or sky-based calibration and give us more accurate and more precise results. Another thing that we can evaluate is the errors on the fit calibration parameters. So those U, once again, for sky-based calibration, we do not fit parameters U, and so we plot the results from redundant calibration and unified calibration. Here, deviations from 0 correspond to calibration errors, and we see that for unified calibration, our fit U's are slightly better. They're better constrained to the position of 0 error.
That's about time, so if you can wrap
Okay. I'll just quickly note that there are other calibration extensions that I didn't talk about here. So a lot of exciting stuff you can do with the unified calibration framework. And then I'll just leave my conclusions up. Thank you very much.
Oh, all right. Thanks very much. Questions? I'm on the wrong page. If anyone has any questions, by all means, raise your hand.
I have a question, but I, for some reason, can't type it into the chat. I wonder if I can just ask a question.
Go ahead.
It looks like your redundant calibration is biased. Are you using like the same, say, like linearization techniques for both the redundant calibration and the unified calibration? I guess what I'm asking is it like an apples to apples comparison, or are you using like log cal for redundant calibration and lin cal for unified?
Yeah, I'm not using log cal or lin cal. So I am not doing linearization in that sense at all. I would say that these are very analytic, simple apples to apples comparisons. I can go into a little bit more detail about how that's performed. It's certainly not the fastest calibration implementation, but it is, yeah, using like very basic, simple optimization methods.
Okay, so it's this, but it's the same for both. Is I guess it looked like, for example, because when you do log cal, you do get a bias on the amplitude. But if you're using the same, then that answers my question. Thank you.
Yeah, good question.
All right, thanks very much. There is one question in the typed Q&A, but again, in the interest of time, I'm going to press us along.
Yeah, I'll go ahead and answer that. Thank you.
But thanks again. Okay. And we'll move on to the next speaker. Nicholas, do you want to take over and share?
Sure thing. Thanks, Keith. All right, let me start my timer. Well, first, thanks to the SOC and the LOC for putting this conference together. It's been great, and I'm really looking forward to seeing more talks. So for those who don't know me, my name is Nick Kern. I am a Pappalardo postdoctoral fellow at the MIT Cobley Institute. I'm part of the HERA collaboration, and I'll be talking today about kind of a side project I've been working on with Adrian Liu on revisiting a technique for foreground subtraction. This is known as the GPR or Gaussian process regression technique. And this is kind of a pet project of ours, and kind of returning to this and trying to understand it is something that we've been working on, and we just put out this paper a couple weeks ago. So I'll just be discussing this paper today. So what is GPR foreground subtraction, or GPRFS as we call it? Well, Gaussian processes themselves are not new. It's just a statistical modeling technique, but they've been gaining traction in the astrophysical literature with certain applications. And in particular, a couple of years ago, the LOFAR team led by Florent Mertens here proposed this Gaussian process technique for modeling and subtracting foregrounds in 21 centimeter data sets. So this is a simulation from that paper showing the power spectrum of their data. In blue, you're seeing the full data set that they simulate, which includes foregrounds, noise, as well as an injected EOR signal in black. And in orange, you're seeing the reconstructed power spectrum after applying GPR foreground subtraction. And what they show is that it's a fairly promising technique in that you can get what seems to be unbiased recovery across all K scales, particularly at low K, going down to K of 0.05 inverse megaparsecs, in the face of what is 4 or 5 orders of magnitude in dynamic range with respect to the foregrounds, which is a really neat result. And since that paper has come out, this GPR technique has become a little bit more widely used in the community, particularly for LOFAR analysis. It was used in the recent LOFAR midband analysis, the recent upper limits at Redshift 9. It's also been used for the LOFAR low band upper limits. It's been used recently, applied to Hera data as for LOFAR. So because this technique is becoming more widely used and popularized, we want just to sit down and revisit this topic and ask mainly, why is it so effective? And how does it compare to existing covariance-based techniques? And as I'll discuss, Gprfs is a covariance-based technique. Okay, so really quickly, what is Gprfs and how does it work? I won't go into too much detail here. You can look at the original Mertens 2018 paper. You can look at my paper. You can also look at this great resource for Gaussian processes for machine learning. The basic idea behind a Gaussian process is that you describe your data. You have a data model which says that each component of your data is described by a joint Gaussian density function. And the idea here for modeling the foregrounds is we seek to ask, what is our estimate of the foregrounds f given our data or conditioning on the data, and under the Gaussian process model, this is itself a normal distribution with its associated mean function and the covariance about that mean function. And if you just go through what the conditioning does to your data model, what you see is that the expectation value for your foregrounds, or your best estimate of the foregrounds, is given as a linear operation on your data vector D. And this is simply weighting the data by the inverse of the data covariance, and then upweighting by the foreground covariance. And of course, in our context, what we want to do, as Johnny Pober alluded to, is we want to form the residual. We want to subtract the foreground estimate from our data. And I'm going to rewrite this in a slightly more illuminating form. I'm going to pull out the data vector and substitute in our equation for the best estimate of the foreground signal. And what we find is that the application of Gprfs can be encapsulated in a very simple, neat linear operator, which I'm going to call capital R Gprfs. This assumes that we know the covariance of the data, at least for it to work optimally. But in a sense, once you know this covariance, you can apply it as a simple linear operator. Okay, so I'm going to take a quick aside and go into inverse covariance weighting and the general quadratic estimator formalism, as I will show, related to this. And specifically, a general quadratic estimator of the power spectrum can be written like this. So I'm going to specify what our data vector here is. Now it is, let's say, the visibility as a function of frequency. So it's some column vector. It could be the visibility as a function of frequency. It could be an image, a spectral image cube at one point of the sky as a function of frequency. But the way that we describe our quadratic estimate of the power spectrum is simply a quadratic combination of our data vectors D. First, we dot them into some arbitrary weighting matrix R, and then we dot both of these into this matrix C comma alpha, which you can think of generally as a Fourier transform and square matrix. And this kind of connects the quadratic estimator to our naive understanding of the power spectrum as simply the Fourier transform and square. And we call this Q our unnormalized estimate of the band power. Now, there's something known as the optimal quadratic estimator, and this has a long history coming to us from galaxy surveys and CMB studies, where people have shown that the optimal estimator, that is to say, the estimator that minimizes the variance on the band powers or minimizes the error bar on your estimated band powers, is achieved when this arbitrary weighting matrix is, in fact, the inverse of the full data covariance, which in our case for 21 centimeter, we're assuming is composed of foreground, an EOR signal, and noise. And this was adapted in 2011 by Adrian to 21 centimeter cosmology from the methodologies implemented for galaxy surveys and the CMB. Okay, so over the past 10 years, we've been learning a lot about the OQE. Some of that was alluded to by Johnny talking about signal loss. One of the things that we've learned is that the window functions can be fairly non-trivial. And what do I mean by window functions? Well, in a sense, what the window functions tell you is how the true band powers map into our measurements. And one of the most important things that the window functions encapsulates is the correlation between the modes related to the the true power spectra, you might say. So when performing parameter inference, when comparing our data to theoretical models, we need to know this window function. And one of the things that Adrian showed is that depending on where you are sampling in k-space, in k-perp and k-parallel, these window functions can be fairly well behaved in the sense that they're spherical and they're compact, but they can also be fairly ill-behaved in that they're elongated and fairly complex. And so this can pose a problem depending on where in K you actually want to measure the power spectrum. The other thing that we've learned is what the inverse covariance is actually doing to the complex visibilities or to the complex data vector. And one way to think of it is effectively as a high pass filter. So this is showing you this inverse covariance kernel in Fourier space. And what you're seeing is that it is effectively suppressing the low K parallel modes where the foregrounds live. And as such, it's going to suppress not just foreground, it's also going to suppress other terms like EOR and noise that live down here, right? And of course, these are the modes of the EOR signal that we really want to reconstruct, because these are generally the ones that give us the highest signal to noise. As such, what we need to do is we need to pass our unnormalized estimate of the band powers through a normalization step, which is a multiplicative step into this M matrix, to get what we call our normalized band powers. So you're effectively renormalizing the impact of this kernel here. And the last thing is that the residual bias subtraction can be very tricky. So what you can show is that regardless of how you normalize the data, there is going to be additional sources of bias. An easy way that's maybe more relatable to think of this is the noise bias. So if you're cross multiplying two data vectors that have the same noise realization, that's going to result in a purely positive real bias that you want to subtract off, which is commonly done. But in the case of 21 centimeter in the presence of foregrounds, there's also a residual foreground bias that you need to subtract. And for our estimator to be free of these excess contaminants, this needs to be very accurate. And this poses a problem because it requires us to know our foreground covariance fairly accurately. In practice, analyses that have tried to implement the quadratic estimator have actually set this to 0 and foregone this step, with the trade-off there being that you are more robust to uncertainties in your foreground covariance, and as a consequence, you're less likely to induce signal loss on your recovered band powers. You can imagine if you've overestimated the C foreground, you're going to actually underpredict your power spectrum. This means that we can be more confident in our results as upper limits, but there's going to be a little bit of excess positive contaminants in our data possibly. So this is a trade-off that we can make. If we think that we know our foreground covariance quite well, then we can subtract this off. But the point being is that in the quadratic estimator, bias subtraction is very tricky and it can lead to signal loss. Okay, so moving back to Gprfs, what's the relationship to the OQE? As I alluded to, we can express Gprfs as a linear operator, so we can implement it as a quadratic estimator. The next question is, how does it relate to the optimal estimator? And I'm going to skip some of the math that I show in the paper. It's really straightforward, just using matrix identities, but you can show that the inverse of the covariance can be refactored into a term that looks like this. So inverse of the noise and H1 covariance dotted with this additional term here, which you may recognize as, in fact, the Gprfs operator. And so what we find is that the OQE operator, what defines the quadratic estimator as an optimal estimator, and the Gprfs operator, what defines a quadratic estimator of the power spectrum as a Gprfs estimator, are very closely related. In fact, generally, right, the H1 covariance is going to be very small compared to the other parts of our covariance, like the foregrounds and the noise. And the Cn is going to be fairly well behaved. It's, in many cases, it will be diagonal. In some cases, it may even be a scalar matrix. So the indication here is that these two weighting matrices are very, very closely related, and all of the caveats and the properties I discussed about the optimal estimator are also going to apply for the Gprfs estimator. So this is an example of applying Gprfs to mock data to demonstrate some of these effects. So what I've done is I've just generated a mock data set, a very simple analytic mock data set with really bright foregrounds, an EOR signal shown in green, and then some noise here shown in black. And then these points is the Gprfs quadratic estimator reconstruction of the EOR power spectrum. The bottom panel here, I'm showing you the window functions of this reconstruction. And notably, what I'm doing is I'm not plotting these points where you might expect based on their actual Fourier mode. I'm plotting them based on where the window functions tells me the band powers are actually sensitive to. And the first thing you see very clearly is that the band powers do not go down below k.1. And that's telling me that because of the fact that I'm using this effectively OQE estimator, the band powers, the window functions of these band powers have been distorted. And they're not really sensitive to a lot of information in the EOR signal below k.1. Now, this, again, is a well understood effect for applying these kinds of estimators. There are solutions to this that come from like CMB and Galaxy surveys. And one of the solutions is to try and partially decorrelate the window functions and restore the information content here at low k. And if you do that, here I'm applying a different kind of normalization that tries to do this. You can see that these band powers are shifted back to low k where I want them to be. The trade-off here is increased vertical error bars. And so there's kind of a trade-off here, which says if you actually want to try and measure the EOR down below k.1, you're going to suffer from larger error bars. And that's not particularly novel, but this is informative, reminding us that this is a problem for the OQE. It's also a problem for Gprfs. And in the paper, we go through some extensions to this that can actually help reduce the vertical error bars here, and particularly by modeling the signal over a wider bandwidth. I'm not going to go into that now. The other effect that I discussed is this whole renormalization effect. So in this case, this is also analytic simulation, but this is a analytic simulation of the LOFAR data set from 2020. So I took their covariance models and I just drew randomly from them. And what you're seeing in blue is that the full foreground plus EOR data set. In pink, you're seeing the actual EOR signal injected, which is much larger than like the noise floor. I'm trying to actually see what happens when you have a fairly bright EOR signal in the data. And in purple, what I'm showing you is if I just formed the power spectrum after applying the Gprfs operator, if I just Fourier transformed and squared the visibilities of this R vector. And you can see that indeed, right? So this Gprfs operator has suppressed the foregrounds, but it's also suppressed a lot of the EOR signal, particularly at low K. And so what we have to do is we have to restore that power. We have to renormalize it somehow. And the quadratic estimator formalism gives us a way of doing this. Like I said, you push your Q vector, which is this purple line, through a normalization step and to get your normalized band powers, which in this case is these dashed lines here. Now, this effect is recognized by the Gprfs papers, in particular the most recent LOFAR limit paper. They also see this, but they treat it differently. And that's in part because this connection of Gprfs as a effective OQE operator, QE, was not made. And the way that they treat this is with a bias correction. And I won't go into the details of exactly how they derive this. It's in their paper, it's in my paper. But one thing that we wanted to show is how sensitive this is to the actual data model you adopt in your analysis. So what I'm doing here is I have the same data set from before. And what I've done is I've now assumed that I know the exact covariances of all my terms, of my foreground, of my EOR, and my noise. But now I'm gonna relax that assumption specifically for the EOR. So I'm going to now adopt a different EOR covariance in my data model than the truth. And I'm going to do that in two ways. So the middle, I've actually matched them. So the EOR covariance I adopt is the true EOR covariance. In the left, I've underpredicted the EOR covariance. And in pink, what you're seeing is the power spectrum from that covariance. The green is the true EOR that I inject. And on the right, you're seeing, is that 2 minutes?
1.5, something like that.
1.5, okay. Yeah, in the right, I've overpredicted the EOR covariance. And what you see is that the black line, which is the LOFAR bias correction procedure, is very tightly coupled to the actual EOR covariance that I adopt. And the quadratic estimator, again, because it doesn't correct as a bias correction, is not as sensitive to this. And so this is just indicating that this bias correction, like we see in the bias correction of the QE, is very sensitive to the actual covariance that you adopt. So in the last 30 seconds, what's the problem here? Well, what that means is that your limits are only as good as the EOR model in your data model, and specifically in the degrees of freedom of that model. So in black, I'm showing the EOR covariance from the LOFAR data model, and I'm showing it with different length scales. This is the power spectrum. And in red, I'm just showing basic, k to the -2, k to the -3 power spectra. And what you see is that given the degrees of freedom of this covariance, it just can't really represent anything that's steeper than k to the -2 in the power spectrum. So why is this problematic? Well, this is problematic because these are the exact kind of models that we're beginning to rule out. So this is from their subsequent interpretation paper. In red, you're seeing the LOFAR limits. The colored lines are the various models explored by the interpretation, and in blue dashed is a representative model that's been ruled out at low k. Now these are flat in delta squared generally, because that's what gives the highest power at low k. But of course, what that means is that they have a k to the -3 dependence in p of k. So this is problematic, and this isn't necessarily an indication that the limits are wrong. It just is an indication that there may be some oversight here for these particular kinds of models. So in the last slide, I want to acknowledge that the LOFAR results do acknowledge this. They clearly state that you need an effective covariance model for, you need a correct covariance model for GPR to be effective. And they even test out a couple of different EOR covariance models before settling on the one that they choose. Unfortunately, none of those actually could reproduce a k to the -3 slope. And furthermore, they do simulated power spectrum recovery tests, which to try to validate their estimator. But again, here they're only looking at EOR models that conform to their EOR covariance. So this doesn't directly address the questions that we raise, although it is a nice result. So that's my summary. So in summary, Gaussian process foreground subtraction is very closely related to inverse covariance weighting and the OQE. Window functions, again, are important for recovering the low K band powers. And we think that the current LOFAR estimator is particularly sensitive to a mismatched EOR covariance. Whether or not that means that there's actual signal loss is unclear, but I'm keen to work with the LOFAR team and other people who have been working with GPR foreground subtraction to try and better understand this in their particular pipeline. So if you have questions, feel free to reach out to me on Slack, and I'd love to take any questions. Thanks.
All right, thanks very much. Any questions? We've got time for maybe one. Hands up in the audience. Danny, go ahead.
Hey, Nick. Can you hear me?
Yep.
Yes.
Okay. Whenever I hear we say these things like, we need to know this exactly, or we need to know this very, very well, or whatever, it raises the question of why can't we just put in sort of what we think our uncertainty is? As you know, we just heard Ruby talking about this, where you put in your your uncertainty about the thing that you're trying to model as well. Is that?
Yeah. So I mean, to be clear, in theory, we need to know it perfectly. In practice, what we really need to know is we need to know it to an accuracy that's better than the dynamic range that we're achieving. And so if you think that uncertainty is smaller than that dynamic range, then you're probably fine. But I think what's useful is to do a Monte Carlo exercise where you actually say, oh, I have some uncertainty about my covariance, and you resample your covariance about that uncertainty, and you do multiple trials, and that gives you essentially a bootstrap, in some sense, estimate of how sensitive your band powers are to deviations in your covariance. I think that's something that we could easily do, and we should be done. Yeah.
All right. Thanks very much, Nick. I think in the interest of time, again, we're going to press ahead. So, Florent, if you want to take over.
Yes. Do you see the screen?
Yep. And we can see you. Go ahead.
Okay. Thank you, Keith. And thanks a lot for the organizer for allowing me to present this work today. So I will talk about the progress we are making in our goal to observe the epoch of renormalization with LOFAR and the cosmic dawn with the NIMFAR radio telescope. So I will present this result on behalf of large team, the LOFAR UR KSP team, and the NIMFAR cosmic dawn KEP team. So despite the title, I will not talk about the true dark age, but the subsequent epoch of the history of universe, namely the cosmic dawn, which is the epoch when the first stars and black hole appeared, and which is followed by the epoch of reionization, when the radiation from these first stars started reionizing the universe. So these two epochs are also key to many fundamental questions in astrophysics and cosmology related to structure formation and evolution of the universe. And they are quite dark in the sense that we have little direct probe of these two epochs. And the most promising method for studying this epoch in detail is still the redshifted 21 centimeter transition line of neutral hydrogen. And in the top plot here, I show you the cosmic dawn and reionization as seen by the 21 centimeter fast simulation. So this shows the brightness temperature of neutral hydrogen as function of redshift. And if you look at the corresponding frequency, you see that it corresponds to low radio frequency observable with LOFAR for the EOR part and with NNFR for the cosmic dawn part. Then there is two main methods to do this experiment. First, you have the global experiment, and then the interferometric experiment. And this is the later, the second type that we are doing with LOFAR and NNFR. So our goal here is to measure the fluctuation of the 21 centimeter brightness temperature, and we are leading or are part of many 21 centimeter experiments. The main one is being LOFAR, which target as a redshift between 7 and 11. With LOFAR, we already observed more than 2,000 hours, mainly on 2 deep field. And in 2017, we published a first upper limit based on 13 hours of data, and we recently published a new upper limit based on 140 hours of observation. Then we have the ACE experiment, which was triggered by the edges detection, and which specifically targets the frequency band of the dip of the absorption profile that was observed by edges. So this is still an ongoing experiment, which use a low frequency boundary of LOFAR. So it is limited in sensitivity and require about 1,000 hours of observation to reach the level of the most extreme theoretical models that will explain edges. So to be able to achieve that fast enough, we observed in a piggyback mode on ongoing observation. And very recently, Barat and Gelo published an upper limit on the 21 centimeters signal at this at the redshift of redshift 18 in a very recent paper. Then still in the cosmic dawn, we recently started a project to observe the cosmic dawn with NNFR, which is a new low frequency interferometer being installed in Nancy. So it has better sensitivity on large scale at this frequency, and we estimated that we need about 100 hours of observation to reach the non-conventional model, and about 1,000 to reach the tip of the more conventional model. And in the more distant future, we are all looking forward to SKLO that promise a great sensitivity to explore the Epoch optimization and the cosmic dawn. So we'll start with our most recent LOFAR upper limit. So the LOFAR EOR is one of the key science projects of LOFAR. So the project takes advantage of the fact that one of the characteristics of LOFAR, which is to combine both very long baseline, which allow to have a very high resolution image, and so allow us to build a deep and detailed sky model. Combine that with a dense core, which provide high sensitivity at large spatial scale. And this is what I show here. So this is a LOFAR supertape, a densely packed area of 12 core stations, and this is a baseline where we use for the 21 centimeter signal. So as I mentioned previously, we target mainly two fields, the 3C1 and 6 field here, and the north celestial pole. And in the rest of the talk, I will only talk about the NCP, the results that we get with the NCP field. So this is a very simplified version of the NCP processing pipeline. So I will not have time to go into the detail of it, but I will just highlight two parts of it, which is how we remove the foregrounds in the LOFAR project, which we are basically doing in 2 steps. And this is a 2 steps that we recently improved to reach our latest upper limit. So in the first step, we need to remove all the detectable point source and result source. So for the NCP field, we build a model made of almost 30,000 sources, and which I show an image here, and you see that it extends to quite a large area of the sky. A lot more than the, if you look at the primary beam of LOFA, it's in the center, and we extend the sky model to quite large area. But because all these sources, depending on their direction, will fill a different ionosphere and primary beam, we have a direction-dependent effect that need to be taken into account in order to subtract this source accurately. So this reduced to a direction-dependent calibration problem that we solve in our case with SAGE-CAL-CO. And in order to make this problem tractable, we need to have additional constraints. And in this case, we constrain the instrumental response in frequency, so to be spectrally smooth. And once you have done that, you have only done only part of the job. At some point, you reach a confusion limit, which is set by the highest resolution you can achieve. And this is still order of magnitude brighter than the signal that we are looking for. So to remove the residual foreground, you need another technique. And in the LOFA project, we use a technique based on Gaussian process relations that Nick just described quite well. So we not have to describe it in detail here. But the main point here is that this method exploits the different frequency covariance of the foreground and the signal, which allow us to build a parameterized covariance model made of these different components. And that way we are able to model the foreground and remove it from our data. So now to show you some results on subtracting our sky model with direction-dependent calibration. So this is a result we obtained on 10 nights of LCP LOFA data. So in total, about 140 hours of data. So on the top plot here, I show the image. So this is wide field image and a zoomed image 4x4. At the top, it's before direction-dependent calibration and sky model removal, and at the bottom, this is after this step. And you see that we do quite a good job at removing all the point source that you see in the image at the top. We do quite a good job, and we are left with confusion-limited foreground plus some low-level residual that you see here and there. So you still need to remove this residual foreground, and to do that, we use, in the LOFA project, we use, as I told you, another method, which is based on the Gaussian process relation. And so this is to summarize this two-step. At the top here, this is the variance of stock psi before direction-dependent calibration. So after the direction-dependent calibration and sky model subtraction, we end up at this level. And with GPR, we basically remove the most frequency current part of the data, and we are done to this level. So down close to noise level, but not so much. So you see that we are still have some gap in between. And this is better seen in this 2D post-spectra ratio, where we plot the ratio between the GPR residual and the thermal noise. And you see that at low K parallel, we still have quite a lot of residual left. And this is basically what set our upper limit. So as Nicolas just described, we make some assumption in building our covariance model for GPR, and of course it is important to test this approach with simulation and injection test. So in our upper limit paper, we do show some result on injection and simulation, and just show you now an extended version of that, extending a bit more the current scale of the signals that we are testing, going up to 20 megahertz basically. And you see that for simulation and for injection test, we are able to recover the injected or the input signal quite well, or have a positive bias. But in this test, we never see a negative bias. So of course, this is not the full story. This is only tested some potential 21 centimeter model, but that shows that we cover with this method quite a large range of the parameter space. So after describing all these foreground removal steps, I show you now the upper limit that we obtain with this pipeline on the NCP field, 140 hours. So this is basically where we started our journey. And this is after all the steps that I described, the upper limit that we achieved. And if we compare that to what we published in 2017 in Patil et al., you see that we were able to improve our upper limit by a factor 10 in variance. So, so what can we learn about the physics of the EOR with this limit? So, of course, this is still quite limited because our upper limits are still relatively high at this stage. But still, we can start discarding some model. And so I show you here two work which have been recently published. One by Guerra and et al., which try to constrain the IGM during the EOR. So they look at a different scenario of IGM, and specifically one scenario with uniform spin temperature. And they found that in this case, they can disfavor model with IGM with spin temperature below 3 Kelvin and with high UV photon emission rate. And in another, okay, so in another scenario that they look at also with non-uniform spin temperature, they can discard model with a large emission region of typical size 3.570 megaparsec, which do not cover more than a third of the IGM and in a cold IGM. And in other work by Mondal et al., they look at constraining the excess radio background, and they found that they can constrain this to be below 9.6 of the CMB at 1.42 gigahertz. And interestingly, this level of excess could still explain the edges detection. So, of course, this is not the end of the story. We always try to improve our processing pipeline. And this is just a flavor of some of the improvements that we are currently doing on the pipeline. Mainly in three aspects, so in improvement in the calibration, in the direction independent calibration, and improvement in RFI flagging also, where we do now do a post-calibration flagging on the full bandwidth to be able to flag fainter RFI, and also flag more. We also look at near field image to find a baseline which are affected by local source, and we are then able to flag this baseline, and you see that we are able to improve our post spectra this way. And lately also, of course, we are working on improving our residual photon removal, and specifically trying to address the points that Nick just mentioned, and to be able to have more physically motivated covariance model, and specifically for the 21 centimeter signal, And we are exploring a different way to do that. And one of these ways would be to have a parameterized covariance train from simulation. And so now I will switch very quickly to the work we are doing on probing the cosmic dawn with Nenifar.
Yeah, only about half a minute left.
Okay, so I will try to be quick, but so Nenifar is a new low frequency radio thermometer observing in the range of 10 to 87 megahertz. So more than half of the plan array is deployed already and working with currently a maximum baseline of 400 meters. And this provides very limited angular resolution, but it's a very compact array, and which make it very sensitive to observe the large scale fluctuation of the 21 centimeters near. So we started observation last summer with the first phase, which only aimed at characterizing the instrument and the field, only into the current limitation of the instrument. And this is the first wide field image that we can make of the NCP field with this instrument, covering between 30 and 82 megahertz. And if you zoom in the center here and include also the small baseline, you see that you can start seeing the diffuse emission in the NCP field. And we have that in stocks I, but also Q and U. And so we are actively looking at characterizing the polarized emission, diffuse polarized emission in this field that way. So this is still ongoing work. But briefly showing some recent results. We started in September of this year, phase 2 observation with a new correlator which improves the frequency resolution and the bandwidth as well, and also with a new remote station which is just here, and which allow us to have a higher resolution map. And this is the first higher resolution map that we can make of the NCP field that way. And the 2 new remote stations will be online very soon, which will improve this image even more. And the first stage after this will be to be able to make deep sky model of the field at this frequency to be then able to calibrate our data. So where
time, if you can wrap up reasonably.
Yes. So I will just keep with that. I will leave you with that image then, which shows the new LOFA upper limit, the new upper limit that we from Delo et al. 2020, and showing some empty box where we will have a new LOFA result very soon. So that's it for me. Thank you.
All right. Thanks very much. We might have time for one really quick question. If anyone had a burning question. Otherwise, I will push it to the coffee session. Okay, let's thank all the speakers again from today. Excellent presentations, everyone. Great to hear about all the progress and work going on here. Bravo from everyone listening. That brings us to the end of this session. So I encourage everyone to head over to the coffee section. I think that's what Joe was just going to ask me to say. So coffee break time. The link is in the schedule of links that was sent around the information sheet.